that means it is moving towards more randomness or disorderedness, right? So in terms of, practicality, let me put some examples and tell me, what do you think about that? What is happening to entropy in these systems? So this is your liquid water, water getting converted into liquid and then gas. Now, can you tell me, based on what you see here, which state do you think is more ordered? Now, be careful. Which state do you think is more ordered?
I would say the first one.
Okay. So guys, this time I'm using a different pen and I hope it works well. So this is solid. Wow, it's difficult to write with this because yesterday my smart pen suddenly became unsmart. I mean, the battery was down. So solid, liquid, and gas. So you said that this was the most ordered system. I will put it as one. How about liquid and gas?
I mean, next would be liquid, then gas.
So in that sense, can I say that the entropy of solid is way less than entropy of gas? Can I say that?
I think so.
So whenever you are going from an ordered system, which is in solid form, when you go to the liquid form, entropy increases. When you go from liquid to gas, entropy increases. But then the increase in entropy while going from these two states, which is solid and liquid, while you're going to the gas phase, is huge, right? The reason is because these molecules are not bounded by any intermolecular forces of attraction. They are free to move wherever they want randomly in entire chamber. So basically, the properties of gas are when you put them in a bigger chamber, they occupy the volume of bigger chamber. That means now they are free to move in entire of the space, right? So always entropy of solid and liquid, they might be very near to one another, right? Solid is always going to be less, liquid is going to be more. But then the change in entropy, the drastic change you will see when you go from liquid to gas or solid to gas, it's going to be huge change, right? Okay, so in that sense, whenever a reaction involves release of gas, so for instance, if I have calcium carbonate, it's known to decompose into calcium oxide plus CO2, right? Now this is solid, calcium oxide is solid, but this is gas. So in this reaction, the forward reaction is associated with increase in entropy on two counts, not one, two counts. See, you start with one equivalent of calcium carbonate, and you end up with two equivalents, one for calcium oxide and one for CO2. So now you're making more molecules out of it, right? So when you make more molecules, you increase entropy. But then it's not just a simple molecules you're making. One of them is in gas form. So even that adds to the entropy a lot, right? So
Professor?
Did we lose him?
Professor?
when the number of molecules Guys, can you hear me? Guys, can you hear me?
Now we can hear you.
Yes, Professor.
Ah, okay, now
Uh,
you can hear me.
I was just wanted to tell you, the Federica is here. I wrote it on the chat, but
Okay, so let me see. Okay, so okay, so looks like you wrote something on the chat. Okay, so sometimes my internet is not stable, right? It's quite unstable, has high energy, right? See, I'm talking into thermodynamics now. See, okay, so in any chemical reaction, when number of molecules increase, entropy increases. And if you have gas as one of the product, entropy increases. See, I'm using those short forms now. This means increases, this means entropy, this means increases, right? Just a shorthand notations, right? Okay. All of you on the same page so far based on this? Okay.
Yes.
So, yeah, go ahead.
Sorry, it says number of molecules and then S increases, and then there's another thing that's circled right next to it. ER, is that?
Which one? This one? Let me put it here. Are you talking about, try to write it with a pen. Are you talking of this one?
Yeah, I can't tell what that is.
This is ES, increases.
Oh, okay.
Okay. So suppose if I give you this reaction, can you tell me what is happening in terms of entropy? When you go from nitric oxide, NO, reacting with oxygen, giving you nitrogen dioxide, can you tell me what is happening? Is entropy increasing or decreasing in this reaction?
Decreasing.
Decreasing. And why is that?
Less molecules.
Less molecules, exactly. So here you start with 2 molecules. Let me try using another pen. This is quite uncomfortable. Give me a second. I'm not sure how long this lasts. Hopefully it will do something. Okay, so we start with 3 molecules here. We end up with 2. Entropy obviously is decreasing. You decrease the number of molecules and you decrease the entropy of in a chemical reaction. So let me write down, show you one more diagram. This is also taken from your book, I suppose, because I had it in my images. So in this case, you can see you start with solid, entropy decreases in a forward direction when you go from solid to liquid to gas. When you go in a reverse direction, entropy decreases. Now, the thing is, if you're looking at a spontaneous process, you should be looking in the direction where entropy increases. When you are looking at a non-spontaneous process, it is where the entropy is decreasing. You don't want to go there, right? So if you want to look for a spontaneous process, your entropy should always be increasing, right? Okay, by that corollary, let me ask you a question. Suppose we start from here, step 1, we go backwards, step 2, we go backward, step 3. Can you tell me what is happening to the temperature when we go in these directions? When I go from gas to liquid to solid, what is happening to the temperature?
Decreases.
Exactly. So temperature is decreasing when you are going from gas to liquid to solid. Suppose this was at room temperature, 25 degrees centigrade. Are these atoms or molecules in solid moving?
Very minimally.
But then they are moving, right?
I'm saying they have to be.
Yeah. So basically, even at room temperature, even if it is a solid, the atoms or molecules in that solid are oscillating around their mean position. They are not allowed to leave their position, but then they are still moving, right?
Yeah.
So still, because of that, there is certain level of entropy associated with that. Now, why is that? Now think about, let me paste one. Let me see where I have that one. Let me show you that. So even at that position, the molecules or atoms are constantly moving like this, right? Although the molecule from outside may look stationary, but then its bonds are constantly vibrating, right? And each of the vibration gives rise to one of the microstates. And you can imagine when you're looking at a solid crystal, you have billions and trillions of molecules arranged in the lattice. And all of them are oscillating, their bonds are moving, they are vibrating, and you can imagine the number of microstates. Now the question is, what happens when I still decrease the temperature of solid? What happens to that movement? Would it slow down or will it speed up?
Can you repeat the question? I'm sorry.
So at 25 degrees centigrade, suppose my molecules and atoms are oscillating at their mean position at a lattice point. If I still decrease the temperature, am I going to decrease their oscillations?
Mm,
Let me see, what do we have on the chat? That's right. So Kellen, you are right. So when you decrease the temperature, you are giving less energy into the system. That means those oscillations will start to slow down, right? So can you tell me what would happen at absolute 0 Kelvin? See, this one is 298 Kelvin. 0 degree Celsius is 273.15 Kelvin. Can you imagine what's going to happen at 0 Kelvin?
yeah, they have to stop moving.
Absolutely. They will absolutely stop moving, right? And this is your third law of thermodynamics. When the molecules stop moving, that means you have reached to the perfect crystalline substance ever known in this universe, right? Now, let me paste one. So let me show you this diagram. This is animation. See, as we decrease the temperature, these molecules were moving and then start to stop, and then they almost stop. They never stop exactly. You see that?
Yeah.
And you can see the temperature decreasing at the bottom. Now, there is a reason for that. Why this thing does not stop. First of all, let me put one figure that's been taken directly from your book. So this is a sort of a phase diagram. In fact, it is a phase diagram, not the way you saw it in your previous chapters. But then here we are looking at a phase diagram from the entropy point of view, right? So when you go from gaseous state to the liquid state, you decrease the temperature, you decrease the kinetic energy of molecules or atoms, and they start to become more and more ordered, and the entropy starts to decrease. At a particular point, at this point, that is where the phase change happens. So what happens in in that time, during that time? The temperature stays constant. We know that when ice melts, there is a phase change. But then at that particular temperature, you are not going to see any rise in temperature, but then system will keep on absorbing energy. You remember that phase diagram, the heating curve that we did?
Yeah.
So we did those kind of heating curves, right? So during the phase change, the temperature does
So-
not change. So if ice is melting at 0 degrees, there will be a phase change, but then the temperature will still be 0. So the same thing happens here. The temperature is constant. You can see it's right there. So if you're looking at water, this has to be 100 degrees centigrade. So in that stage, when the phase is changing, but the molecules are getting really close to one another, they are going from gaseous state to the liquid state. So it's basically the entropy is decreasing drastically in that region. And that's why you see this.
Professor,
Yes.
saying that when it comes to these phase changes, they're happening instantaneously, but it has to reach a certain temperature in order to shift all the way up from solid to liquid. And it'll slowly get there and then it'll move automatically and entropy will jump automatically.
Yes.
Okay.
Yeah.
Got it.
So there will be a gradual rise. And once you hit that phase change point, at that point, the temperature is not going to change, but then the phase is going to change. And it's going to happen like in a fraction of a second.
Mhm.
The
Understood.
same thing. Okay. Now, did you remember when I mentioned over here? Let me go back. I mentioned that when you go from solid to gas, there's a huge change. When you go from liquid to gas, there's a huge change. But then from solid to liquid, that's not a big change. You can see here. There is a small change here, but then a huge change here. Now, if you go from gas to liquid, solid to liquid straight away, when you are doing a sublimation process, look at the change that you can get. So you can have a sublimation process, just like your dry ice goes from solid to gas in one step, right? You don't encounter liquid because you are well below the triple point, right? So think about the triple point at this moment, right? But then whenever the phase change happens from solid to gas, there's a huge change in entropy. But then when you go from solid to liquid, there's a small change. Okay, so this was about the phase change. Now, when you are in the solid state, you keep on decreasing the temperature and the entropy keeps on decreasing. And at a particular moment, you reach a stage where there can be only one probable state, the micro state, right? Now, think about it. If I write this thing as KLNW final minus KLNW initial. Can you tell me if I do something like this, what would be the entropy? Any guess on that? So when I reach at absolute zero, how many microstates are going to be there in that case?
Can you remind me what microstates are? Sorry.
So microstates are the most probable state at a particular temperature. So when you are at 0 degrees, there can be only one microstate, which is the perfect crystalline state. So that one, this WF, is going to be 1. So at 0 degree Kelvins, this is going to turn out to be ln1, and that's going to turn out to be 0. So entropy will turn out to be 0. That's what you see here in form of limit. Now the question is, can you reach absolute 0? And why is that?
Professor?
Yeah, I'm here. I'm just listening what you want to say. So why does entropy, why does the temperature stop well above the 0 degree Kelvin? Why can't we reach 0 degree Kelvins, which is negative 273.15?
Is it even possible within our atmosphere?
We can get up till negative 270 Kelvins. I've done the reaction at negative 195 with the liquid nitrogen. So liquid nitrogen can get to negative 195.
So you can get to absolute zero, but it can't stick.
You can't get to absolute zero. That's what I'm saying. You can't get there.
You cannot.
No, you cannot. Question is why? Why cannot we get to that temperature? Any idea about that? See here in this animation, let me put it on the second slide. Do you see this term here, which says limit, temperature tends to 0, entropy equals to 0. So it says that when you decrease the temperature, when it is approaching 0 degrees, your entropy becomes equals to 0. But then this limit is, it's a very, very interesting mathematical function in that way, because it tells you that you are trying to reach 0, but you cannot reach 0. That's what it means. So let me ask you a question in this way. Now, this one is quite a little bit mathematical, but I will try to break it down in form of a concept. Suppose you start from point A to point B. Now, suppose your first step is this, half of this, right? So you are at A by 2. Now, can you tell me if every step that you take should be half of your previous step, would you be able to reach step B, point number B? Every step you take from step A should be half of your previous step. Can you reach B?
Why wouldn't you be able to eventually?
Let's see. Suppose this one is 10 kilometers or 10 miles. Just think in this way. My first step is 5 miles. My second step would be 2.5. My third step is 1.25. Would I be able to reach step point number B?
Well, no, because when you reach point number B, there's no half amount from before.
In fact, you won't be able to reach B. You will get really close to B, but you will not touch B. Because if you add up all these numbers, so your first step is 5, second step is 2.5, the third step is 1.25, and the fourth step is still half than that, and it will become half and half, and it will become so small number that you do get close to B, but you will never reach B. It is exactly in the same way. You try to get to the 0 degree, but then you cannot reach absolute 0 kelvins. This works exactly in the same way. Now, this is based on the mathematical concept, the one that you see here. I'm explaining you that. But on a physical level, what exactly is going on? Now, think in this way. When our universe was formed, have you guys heard about the Big Bang Theory?
Yes.
So when it was, when our universe came into existence, there was a Big Bang, huge amount of energy was released, right? And this entire universe started to spread, right? Now, in this entirety, the one which you see in outer space, we still have a microwave radiation spreaded evenly all across the universe. You cannot get rid of that energy because it is there. It's always there. So it is something like you are living inside the water. You cannot get rid of water. It is exactly in the same way. You can get up to 3 kelvins. I suppose it's, I think, 3 or 2.15 kelvins, but then you cannot go below that because that amount is present. That amount of energy is present everywhere in the universe. Many times you would have seen, we call it a 0-point energy. And there have been many movies on that, right? We call them 0-point energy modules, the 0-point energy, engines, right? So it's a lot in the popular sci-fi culture, right? They talk about 0-point energy because if you were able to harness that energy, in a sense, you have access to unlimited energy in this universe. It's everywhere. You just have to tap into that energy and get it. Unfortunately, we don't have any means to do that, right? But then it is there, scientifically proven. And from there, we speak about that dark matter, dark energy, those kind of things actually came out from here, from the third law of thermodynamics, right? But then don't worry, I'm not going to ask you about the dark matter and dark energy in your exam. So just relax, right? But then the point is, if your entropy at absolute zero is 0, right? Because there is only one microstate available. That means the entropy of your system higher than that, higher than absolute 0, will have certain amount of entropy already associated with it. That's where I'm going to show you one table, and we are going to do some entropy calculations on that. So suppose when we are thinking about the standard entropy, the one which is at room temperature, for all compounds and substances, it will be associated with some entropy. Why? Because these compounds or molecules are moving. They are not just moving in space, but then their atoms are also vibrating around each other, right? So they are associated with entropy. So this one, standard entropy, essentially tells you the change in entropy from your standard state. So suppose if your standard state is the final step, I will say final minus S initial. Now, if your S initial is entropy at 0 Kelvin and S final is your entropy at 298 kelvins, which is a room temperature, whatever entropy you get, the value that you get becomes the entropy of that substance. And we call it standard entropy, standard molar entropy. Now, for instance, for hydrogen, that turns out to be 130.6 joules per Kelvin per mole. But then what is the entropy at absolute 0? That is 0. We know that. So this turns out to be 130.6 joules per Kelvin per mole. This is how we calculate the standard entropy. Now you know where it actually came from, right? So we got the standard entropies for all these substances. Can we use it to do a reaction, find the entropy change of a particular reaction? Answer is yes. Why? Because entropy is a state function. So if we know the initial state of the system, we know the final step of the system, in theory, we should be able to calculate the change in entropy. For instance.
Professor,
Right? Yes.
entropy initially you said is absolute 0, but I thought we can never reach that point. So how could it ever have started there?
Okay. Physically, we cannot reach there, right?
Theoretically, you're saying?
Yeah. So physically, we cannot reach to this point. But then it does not mean that it is not existing. It is there.
Okay.
We don't have means to get there, but then it is there, right? But
Yeah.
then if I want to find what was my starting point, that was 0. What is my endpoint? That is your final point. I cannot get there, but then it is there. So whenever I find the entropy, my reference point is always that. And then I do it based on my reference point. And at my reference point, my entropy becomes 0. Make sense?
Yeah.
Okay. So suppose if I'm doing this reaction, I mix hydrogen and oxygen together and I get 2 water molecules. Now, is it a balanced equation? It is not. How do I balance it? I put 2 here. Now, I want to know what is the change in entropy when I go from my state A to state B. Now, interesting thing, this is in gaseous form. And suppose I'm forming water in the gaseous form. Do I have the entropy for hydrogen gas? Yes. Do I have entropy for oxygen? Yes. Do I have entropy for water? Answer is yes. All of them are provided to me. So how do I use it? Well, the change in entropy of the system is entropy of my products minus the sum of the entropy of my reactants. So first of all, as I said, entropy is a state function, but then entropy is also intensive property. That means it depends on the amount of substance that you are taking. Here you are taking 2 moles of hydrogen, 1 mole of oxygen. On this side, you're forming 2 moles of water. So you're going to multiply these numbers by the coefficients of that particular compound. So when you look at the products, entropy for water is 2 multiplied by 188. That's going to be 188.8 minus the entropy of my reactants. So for hydrogen, it is going to be 2, 130.6 plus, what do I have? Water, oxygen, 200.5.0. Can you do this math for me? Negative 88.6. Okay, that makes sense. So let me go, let me expand this a little bit so you can see what we have on the previous slides. Okay, so the change in entropy was negative 88.6 joules per Kelvin per mole. Now, this negative sign tells you that you are decreasing the entropy, and which makes sense. You started with 2 moles of hydrogen, 1 mole of oxygen, and you got 2 moles of water, right? So you started with 3 moles, and now you're getting 2. Makes sense. So you are decreasing the number of moles, and you can see the decrease in entropy. Now we want to know what happens if you convert your gas into liquid water instead of gaseous form. Let's see that one. And then we will see what is the change in entropy when you go from gaseous water to liquid water directly without encountering this reaction. Let's look at that one. So this time, find me the change in entropy when you are going from gaseous reactant to liquid water directly. And you're going to use hydrogen, oxygen, and liquid water. Find me the change in entropy. negative 326.4.
That's what I got.
Okay, that looks correct to me. So negative 326.4, right? So now you see, when you go to the gaseous form, there is a change in entropy, but not to the extent when you go from gas to liquid. There's a huge drop in entropy. And now you can imagine this change. See here, you can see that big drop. You don't see that big drop when you go from gas to gas reactant, right? Okay, now let's see if this holds true when we are looking at entropy as a state function. What do I mean by that? Oh, put it here, gas. This is gas. And I'm going to write down the second reaction. Now, entropy change for the first one was negative 88.6. For the second one was negative 326.4, right? What happens when you go from here to here? What is the change in entropy based on this equation? It decreases, but then by what number?
What do
So
you mean
now
by
this,
number, Professor?
so this one is your final. Now this one is your initial. I want to know the change in entropy when you go from here to here. You found the entropy for this one. You found the entropy for this one. This is that. This is that. I want to know the entropy over here. By what number? Give me the number. Negative 237.8. That makes sense. Okay. So I'll just copy this over here. So in this case, what you guys did was you had entropy of final minus the entropy of initial, and you found negative 237.8. Is it what you did, all of you?
Yeah, just on the difference between the two of them.
Okay, that makes sense. Now, let me write down this equation. Use now these numbers and tell me why they don't match with what you just found. Because if they don't match, that means we got a problem. Okay, so you got entropy of your reactant, which is 188.8, which is gas. Entropy of product, it is 69.9. Now, can you find me the change in entropy using this equation?
It's negative 118.9, Professor.
But then isn't it that entropy is a state function, does not depend on how you get to that state? Here, we went from hydrogen, oxygen in gaseous form. We made the gaseous water, and then from there, we went to the liquid water. But then why do we have entropy for that reaction as negative 237? So you just found this one was negative 237.
That's wrong.
Are you sure?
Yeah, because it's 2H2O. It's not negative 118 is just half.
So is it wrong or is it something else?
Well, it depends. If you're going from just H2O gas to H2O liquid, then you have negative
Mhm.
118. But if it's 2H2O,
Mm-hmm.
wrong. It's just different. It's a different equation.
Yes, it's a different equation. It is not wrong because, as I mentioned, entropy is, besides being a state function, it is also intensive property. It depends on how many molecules you are doing. So you have two molecules in this process, so this makes sense. But then here you used one molecule or 1 mole of this and 1 mole of your liquid water. So your answer is per mole. So keep that in mind, that entropy is intensive property as well. Okay, so any doubts so far before I go to the next part? So we're going to expand on entropies. Okay, so think about, say for example, the entropy. I will give you an example of entropy of diamond and graphite, a very classic example that we give to our students. So entropy for diamond is 2.38 joules per Kelvin. So let me write down here. Entropy for diamond, 2.38 joules per Kelvin per mole, and entropy for graphite is around 5.74 joules per Kelvin per mole. Now, if I want to go from diamond to graphite, can you find me the change in entropy of this system and tell me whether this process is spontaneous or not? Because for a spontaneous process, entropy increases. For non-spontaneous process, entropy decreases.
Professor, would it be like a one-to-one question?
Yeah, it's a one-to-one. Yeah. So when you say 3.36, is it positive? Is it negative?
Positive, Professor?
So what do you say about the process? Is it a spontaneous process or a non-spontaneous process?
Non-spontaneous.
Right, entropy is increasing. You are going from
Sorry, the
more, yeah. So
it increases.
it's a spontaneous process. So if you have a positive entropy, 3.36, that means you are dealing with a spontaneous process. So diamond has inherent tendency to go to the graphite. It wants to go there. But then if you want to convert graphite into diamond, you need energy. By the way, do you guys know how we make those diamonds from graphite? Any idea about how we do that?
Nope.
It's quite interesting. So generally what we do, we take iron, we melt it like this. And in this iron, we mix graphite. And then we cool down this iron very, very, very fast. Within the fraction of a second, we cool it down. When we do that, the graphite inside in the mixture undergoes a pressure changes because now iron atoms are trying to form the crystal, and they are trying to impose a lot of pressure on each other along with the graphite. So graphite under that pressure starts to get converted. It will start to form diamonds. It will start to spit out diamonds. It literally does that. You can see the diamonds coming out, as if this whole matter is spitting out diamonds. So I've seen this process. I mean, it's a fantastic one. You can see those, and you can also hear that sound. Those sounds like stones coming out, but then those are diamonds. But then those are cheap diamonds. I can tell you that they are not the one that you buy for millions of dollars. They are not the ones. They are of a lower quality. You can break down those diamonds quite easily. Not the pure diamonds that you get in nature. So just to let you know. So that's the effect of the pressure on entropy. Okay. Having said that, let's see one more equation. So I will just write here, when entropy is greater than 0, we are looking at a spontaneous process. When entropy is less than 0, that means you are looking at non-spontaneous process. What if entropy is equals to 0? What is happening then at that time? You go from A to B, there is no change in entropy. That means your system is in equilibrium, right? There is no change in going back and forth. That also means that you have a number of molecules on left and on the right side, they are the same. The matter, in the sense that when you are looking at the state of the matter, is also same. There is no change in the state of matter, because if there's change in state of the matter, then you will see the change in entropy. So this process at 0 is at equilibrium, right? But then let's look at another example. We studied about enthalpy, right? Now, enthalpy greater than 0, can you tell me what exactly is that? Is it a spontaneous process? So I'm going to give you 2 examples. You tell me what is going on when you have enthalpy, which is greater than 0. Okay, so greater than 0, it's a non-spontaneous process. You are right, Kellen, on that. That process is endothermic reaction. See, now I'm speaking in terms of energetics, right? And if it is less than 0, that you're right, you are giving out energy. That means you are coming down the hill. That means your reactant had more energy than the product. You are going from less stable to more stable system. In that case, it's a spontaneous process. You don't have to supply energy to come down. You need to supply energy to go up, right? So enthalpy greater than 0 is non-spontaneous, and enthalpy less than 0 is spontaneous. So I'm going to write here, okay. Now you see, try to compare with entropy. How do we define entropy in terms of enthalpy? Anyone? We spoke about this before. Who wants to try this one? Do you guys remember? I mentioned entropy equals to Q reversible by T. That's where we started. All of you remember that?
Yes.
Now, if a process is occurring at the constant pressure, what happens to Q? If a process is occurring at constant pressure, what happens to Q? Keep in mind, if a process occurs at a constant pressure, what happens to Q? You have answer right there. It depends on temperature. Yeah, that's true. But then I just want to know what happens to Q at a constant pressure. Guys, I'm waiting. It is on one of these slides. I'm not going to go back. Let's see if you can answer that. Guys, remember I mentioned any process occurring at a constant pressure will convert your energy into enthalpy. Remember that one? So if Q reversible occurs at a constant pressure, it turns into enthalpy. So I should be getting something like this. So far, so good.
How does that work, Professor?
We went through this in the last lecture. Should look into what we had last time. We went through the constant pressure. We went through in details about that. If you have any doubts, you can stay back and speak with me in the office hours. But then you should know about that one. If you are working at a constant pressure, your enthalpy becomes, your energy changes, which is Q, heat changes, becomes enthalpy, right? So if this becomes enthalpy, I can simply convert Q reversible equals to delta H over T. Now, why do I need to use that? Now, look here. We have the spontaneity of a reaction in terms of entropy. We have spontaneity in terms of enthalpy, right? So we have two different criteria. One is telling me how ordered or disordered a system is. The second one is telling me whether I have more energy or less energy into the system. Can I have a common equation which can connect both of them? Answer is yes. Let's see that common equation. So the delta S, which is the entropy, oh, my pen stopped working. I'll use another one. So my handwriting is going to be bad now. Oh, it's fine actually. So delta S universe equals to delta S system plus delta S surrounding. That should be my entropy of the universe. It should be entropy of system plus entropy of surrounding. It's simple as that. Now, when I think about entropy of surrounding, it does depend upon the entropy of system. For example, if my system is expanding, my surroundings are contracting. If my system is contracting, my surroundings are expanding. It's just like when I am giving out energy, the surrounding is absorbing energy. When I am absorbing energy, my surroundings are giving out the energy to me, right? So system and surroundings work in that sense. All of you agree with that? So in sense, I can write this term in form of entropy, but an entropy of the system. Now you would wonder, I can simply write down negative entropy of system, right? So if I incorporate these two values together, I will get delta S universe, which is going to be 0, which makes sense because entropy of universe stays constant. That was supposed to be for the reversible process. But now if you are not dealing with a reversible process, entropy of universe keeps on increasing, right? Okay, so how do we account for that one? Well, I'm going to convert this term into delta H, the one that I have it from here. So see what happens. So this is delta S system plus, I will write down here negative delta H system divided by temperature. And that becomes delta S universe. I'm going to expand this equation more. I'll just rewrite the same equation. That's equals to delta S system minus delta H system divided by temperature. Now, if I multiply this entire equation by negative temperature, see what happens. Negative T delta S, this is for the universe. That is equals to negative T delta S for the system. And this is going to be now positive delta H, because if you multiply this term by negative T, this is what you're going to get. This one is your Gibbs free energy, delta G. That's equals to, I'm going to rearrange this equation, having positive term before and the negative term after that. This is a very classic equation, which actually connects your enthalpy and entropy in one equation. So let me now think about it. For a spontaneous process, what should be the value of delta G? More than 0 or less than 0?
Are we talking in enthalpy?
Yes, that's what I have highlighted.
Less than 0.
So this is negative. For a spontaneous process, what should be entropy? More than 0 or less than 0?
More.
More than 0. So this should be positive. If I have a positive value over here, and if I multiply that positive value with a negative sign, so I should be getting negative and then again negative. So for a spontaneous process, this should be negative. If your free energy, which is delta G, is negative, that means you are dealing with a spontaneous process. So let me write down the criteria for this.
Professor, what does G stand for?
Free energy, Gibbs free energy.
Gibbs free energy.
So if your delta G greater than 0, you are looking at non-spontaneous process. If delta G is less than 0, you are looking at spontaneous process. If delta G equals to 0, the system is at equilibrium. So let me paste one table for you, which is going to be quite helpful. This is taken from your book directly. So let me, okay. Take this one. This is going to be better. Oh, yeah, this is better. So enthalpy negative, entropy positive, free energy is negative, which is a good thing. Spontaneous at all temperatures because you have a temperature component in this equation. When you have enthalpy, which is positive, that means you are dealing with an endothermic reaction. You're going up the hill. Your entropy is negative. That means you are making the system more ordered. The net result of delta G is actually positive. So that reaction is non-spontaneous at all temperatures, right? So here are the two equations. You break down ozone gas into oxygen, that's a spontaneous process. But to reform ozone is a non-spontaneous process. Now, there will be certain circumstances where one of them will be positive and one of them will be negative. For instance, when we think about enthalpy being negative, that means it's an exothermic reaction. But then entropy is getting towards more ordered system. So what happens in that case? Let me put that equation. Delta G equals to delta H minus T delta S. If this is negative, which is good for the system, we want the reaction to be exothermic for it to be spontaneous. But when this becomes negative as well, that means here your entropy is decreasing. You are going from less ordered system to the more ordered system. This whole term becomes positive. Why? Because the negative entropy multiplied by negative sign becomes positive. So we are going to do some examples on that, and then you will see that effect, right? So this multiplied by temperature is going to make the things worse. So when you increase the temperature, in this case, you are going to make the system less and less stable and less spontaneous. So let's do one example on that, and you will see that effect. So you have a reaction where you have ammonium nitrate, and you are using this ammonium nitrate at a room temperature. You're putting it in water and dissolving it. So the reaction would be ammonium nitrate giving you ammonium ion plus nitrate ions. And these are in all aqueous form. This is solid, but then this is aqueous, and this is aqueous. Step number one, you need to find the change in enthalpy, delta H. But then since we are doing it at a room temperature, we are dealing with standard enthalpy. Okay, and how do we find the standard enthalpy for this reaction? So this is enthalpy for reaction, R stands for reaction. That's going to be sum of the enthalpies of my products minus sum of the enthalpies of my reactants. Do we have those values? Answer is yes. We have the enthalpies for the products, the standard enthalpies for the products, and we have standard enthalpy for the reaction. Can you find me over here? Are you sure? Mm-hmm. So your standard enthalpy for products, that's going to be 205.0 minus 132.51, because these two are having opposite sign. When you add them, still is going to be, you are subtracting, minus the enthalpy for my reactant, that is negative 365.56. So I think Abraham got, let me see, 438.06 positive.
That's what I got too, positive.
That's right. So it's a 438.06. And this
Zero
is
five for me, but
okay.
I don't know if it matters.
So we can keep this in kilojoules. So energy is given in kilojoules. So just to let you know. And this one, entropy is given in joules per Kelvin per mole, just to let you know about that. Okay. So here you found it was 438.06 kilojoules. Okay, that makes sense. Now let's go for entropy, change in entropy. I'm just going to copy this whole table. You just found your enthalpy. Now we are going to find the second component, which is entropy. Again, entropy here, since we are dealing with a standard state, I'm going to put that small 0 on the top, which says it's a standard, which is room temperature and 1 atmospheric pressure. That's going to be entropy of your products minus the entropy of your reactants. So that's going to be equals to, what is your product? 113, 146. That's going to be your product. So 113.4 plus 146.4. This is your product minus the entropy for the reactant is 151.08. So looks like 108.7. All of you got that answer? Now the units are joules per Kelvin per mole. So now we have entropy change for a reaction. We have entropy change enthalpy change of a reaction. Now, can you tell me, based on enthalpy, is this a spontaneous or a non-spontaneous reaction? It's a non-spontaneous, right? It's a positive sign. Based on entropy, is it a spontaneous or a non-spontaneous reaction? Spontaneous. So now we see these two effects working against each other, right? One of the processes making the reaction non-spontaneous, which is enthalpy, it's an endothermic reaction, and entropy is favoring it. So this reaction is entropically not favorable, enthalpically not favorable, but entropically favorable. Keep that in mind. We use this term a lot. Entropically favorable. That means it is spontaneous based on entropy. Entropy is leading that reaction. It wants to happen, but enthalpy is not letting it do. But then these are the, when you put them in that free energy equation, that actually determines whether your reaction will occur at a first place or not. So let's look at that one. So suppose now I have free energy of this reaction. That's going to be delta H minus T delta S. We know the value of delta H, which is 438.06 kilojoules. We know the temperature. What is temperature? It is 298 kelvins. We know the change in entropy. What is that? It is 108. Let me move a little bit on the left so I can have enough space to write. Okay, then this has to be multiplied by 108.7 joules per Kelvin per mole. This is kilojoules per mole. So Kelvin and Kelvin will cancel out, right? So now I'm going to get energy in joules per mole. Can you find me this answer and tell me whether reaction is going to happen at a room temperature or not? And be very careful with the units. Be extremely careful. Anyone with the answer? So Abram, the one that you got was for Did you change the units?
What do you mean, Professor?
Look at the units. This is joules. This is kilojoules.
Oh, hold on. Let me do it again.
Mm-hmm.
I got a much higher number, Professor.
Mm-hmm. So what is that number?
405,667.4.
Okay. So are you sure of that one?
I guess as sure as I can be, you know.
So this is 438.06 kilojoules minus 32.2 kilojoules, because what you got was 32,184 joules. If you convert this into kilojoules, this is what you have. Now, what is the answer?
Right. $405.86.
Now, when you think about this data, entropy, free energy is positive. That means at room temperature, this reaction shouldn't happen. And now we know why it's like that, because enthalpy is dominating factor over here. Yes, entropy is increasing. It is helping this reaction, but entropy is not helping. Enthalpy is not helping much. It is actually working against the spontaneity. So you can do this reaction eventually when you start to increase the temperature from 298. When you increase the temperature at a certain point, this number will become equals to this number, which means that at that point, your free energy will be zero. That means your system will be at equilibrium. Higher temperature than that, you are going to look at a spontaneous reaction. Let me go for one more problem, which is going to be similar to this. Here, I have provided you, let me move it. Why it's not letting me move that? Okay, now this is good. So in this case, you are generating, let me make it a little bit bigger. Okay, so in this case, you are generating ammonium chloride. Enthalpy is given to you, entropy is given to you. Find me delta G, tell me whether the reaction is spontaneous or not at room temperature. So start from room temperature and tell me about that. I'll write down that equation for you.
Professor, do we want it in kilojoules or joules?
No, I want the answer in kilojoules. And be very careful. Again, the entropy is given to you in form of joules per Kelvin. Be extremely careful with that. Also be careful with the temperature. It's given to you in degree centigrade. You need to convert it into Kelvins because these are in Kelvins. Entropy is given to you in Kelvins. So extremely careful over there. So your enthalpy is negative 176.0 kilojoules. That means this reaction is enthalpically exothermic, should happen. When you look at entropy, this reaction is not spontaneous. It does not want to happen. Look at the number of molecules. So you are going from 2 to 1, number one. You are converting your gas into solid. Again, entropically, it is not favorable. You're going from highly disordered system into highly ordered system. So entropically, this reaction is a nightmare, right? But then enthalpically, this reaction is awesome. It's giving out a lot of energy. Your products are more stable than the reactants. Now let's put them into the equation and see whether this reaction can happen or not. So 298 kelvins is your temperature. Multiply that with your entropy, which is negative 284.8 joules per Kelvin. What do you get? It is negative 176.0 kilojoules minus, are you guys getting 84870 joules per Kelvin? Are you guys getting that? Are you guys getting this one?
You wouldn't want us to convert it to kilojoules before we do that part?
Yes. So after this, you're going to convert it into the kilojoules, and then you will go for the next step. So I'll just put it here, negative sign. Now that makes sense. So that's going to be negative 176.0 kilojoules plus 84.87 kilojoules this is what I got. Negative 91.13. It's quite difficult to write with this pen. 1.93, that's what Roberto got. Okay. So it turns out that this reaction still can happen, despite you are going from gas to solid. But the question is, what happens when I increase the temperature? Suppose this is the reaction that's happening at a room temperature. Now, suppose if I increase the temperature from 298 to 398, let's make it 400 kelvins. Everything stays the same, but now I'm doing this reaction at 400 kelvins. Tell me what's going to happen. I'll just copy this problem one more time. Find me instead of that, use 400 kelvins. Oh, no, not 400. Yeah, you can use 400 kelvins, yes. Oh. Let me see what we have. This time, negative 176.0 kilojoules. That was the energy. Minus, this is going to be 400 kelvins. And your entropy stays the same, negative 284.8 joules per Kelvin. What do you get? I think Abram already had an answer. Negative 62.08. Oh, okay. So negative 62.08. See, now we made our reaction less spontaneous. We went from negative 91.3, we went to negative 62.08. right? Okay. Next thing, do it at 600 kelvins. The same one at 600 kelvins. So delta G at 298, you found it was negative 91.3 kilojoules. Delta G at 400 kelvins, that was negative 62.08 kilojoules. Well, delta G at 600 kelvins, that is negative 5.15 kilojoules. That's what we got. Okay, I can see that. How about at 800 kelvins? It's positive 51.84. Yeah, see? So you just converted your a spontaneous reaction into a non-spontaneous reaction by changing the temperature. That is exactly what just happened, right? So around 600 kelvins, that is where the threshold is. That's where your reaction is about to get non-spontaneous. And on a conceptual level, that makes sense. See, when you are increasing the temperature, you want your reaction to be in the gas, you want your substance to be in a gaseous form. That's where the spontaneity is, right? The molecules have enough energy to get into the gas phase, and you're trying to get them into the solid phase. So those are the two opposing forces which are happening based on the concept. But now you see, based on the numbers, that it is actually happening. At 800 kelvins, molecules have so high and kinetic energy, so enormous energy, that they do not want to come together and do the reaction. They want to stay outside this. So reaction becomes non-spontaneous. So Abram, here we are not decreasing the entropy, we are increasing the free energy. And when you say that temperature decreases with decrease in the entropy, can you elaborate more on that?
Can you repeat that? What did you say?
So you asked a question on the chat that I thought the temperature decrease with decrease in entropy.
Right.
What are the rules? Okay. Going back on this one. This one is telling you what is the entropy of that particular stage, right? So when I think about this as solid, I'm speaking about that particular micro state. So this entropy corresponds to a particular micro state.
Mhm.
So now when you increase the entropy, when you increase the temperature, yes, there will be change in entropy of a substance. But then I'm speaking about only one specific micro state for this particular reaction. So that stays the same. So suppose if I have a solid crystal and if I have molecules arranged in a particular fashion in that crystal, you increase the temperature, you are going to change the entropy, but then that is a different microstate. Entropy of this one is the same. The one that you are referring to is a different microstate. We are not looking at that state. We are concerned about this state only. Okay, so having said that, one last equation for free energy, which is delta G equals to minus RT ln K. Now, K is your equilibrium constant because we just said that at delta G equals to 0, we are looking at an reaction at equilibrium. So there should be some connection between free energy and equilibrium constant. And this is that equation. So if you know free energy, so say, for example, if you know free energy at this, can you find equilibrium constant? Answer is yes. So suppose this one is 51.84 kilojoules. You know R, which is 8.314 joules per Kelvin per mole. You know temperature because you just use that temperature. It's 800 kelvins. Multiply that with ln K. Can you find ln K? Answer is yes. Can you find K? Just take inverse log of that and you will find K. Can you do this problem right now? But make sure this is in kilojoules, this is in joules. And you need to have a negative sign as well. See, I'm getting 4.1 10 to the power negative 4. This is what I'm getting.
Reza, how do you do inverse log again or inverse ln? Okay, got it. Yeah, I got the same thing.
So this one should be, so if this is, let me write down in this form. So if this is your ln K, and if you get, say, for example, X, your K will be e raised to X. That's how you can write down. So 10 to the power negative 4. And you can see equilibrium constant if it is 10 to the power negative 4. It is more towards the reactant than the product. Okay, guys, so we will stop here for today. I'm going to upload the exam for this chapter. By the way, you guys can see the quiz on your end for this chapter and electrochemistry.